Hey, welcome back to part 3. This is geometric sequences, and I wonder, just looking up at all these sequences we've got here, can you find one that is different from the others? And what are the properties that most of them have got? There are in fact 5 that are very like each other and one that isn't. I'll just give you a little moment now to actually spot that, so you might try and pause the presentation now and have a look at which one is the odd one out. Okay, let's have a look at them. This was the odd one out down here because this is arithmetic. We've got a common difference happening here. Can you see it? A common difference. And all the others are slightly different. Let's go and look at the one up the top here. What do you do to 1 to get 2? You times it by 2. And does that pattern continue? Yes, it does. Can you see that there seems to be a common ratio or multiplier here, a constant multiplier? So here we're multiplying by 4, and yes, that's connected by multiplying by 4. So this looks very much like a common property for these 5. You multiply this by -2, and then it would become positive. So just put multiplication there, by positive 8, and then multiply by -2 again, -16, then plus 32. Okay. Are they all the same? Here's another one, multiplying by -3, and then by another -3. Can you see the alternating signs? Because you're multiplying by a negative. What about over here, this one? 5 times 3 is 15. 15 times 3 is 45. 45 times 3, 135. So welcome to geometric sequences. What they have is a common multiplier, or there's a common ratio between terms. In other words, the nth term divided by the one before comes to a common ratio. Or we might like to write that any term is r times the one before it. So that would be a recursive way of writing the information for a geometric sequence. Okay, can you see what a possible way would be? Let's go up here to this one to get a explicit formula for the nth term. What would the nth term be? Well, I've gone back and used ANs. Should be using mu's. Mu n is mu1 times some r's here times 3. And how many times do you do it? Well, it's 1 less again, isn't it, than the number of the terms. So the third term has only had 2 multiplyings. Only 2 multiplyings. Because the first term doesn't multiply by r yet to get the next one. So again, it will be 1 behind the number of the term. Can you see that? We're going to have a look at that again in a minute. But there's a lot you can start to see for yourself in these sequences. I really do want to switch from Pearson's notation here and just go to this, because that is the IB way of looking at it, mu instead of a. Doesn't really matter. You can call your sequence anything, but that's the idea there. And we'll see that from the information book down there in a minute. So come down with me and let's have a look at what Pearson's have defined this as. This is taken from their new textbook for the new course, first examined in 2014. So here we are, examining the following sequences and the most likely recursive formula. So that's what we've been doing. This is a common factor being times here, a common ratio. We're timesing by 2. So therefore, any term is the preceding term times by 2. Just remember, mu n take 1 is the term before mu n. And so it would be if you use the A notation. What about this one here? Here we go, coming along here. What are we doing? We're multiplying by 9. So there it is. Any term is a term before times by 9. And we should put for n greater than 1 because you can't, you can only start at 1. N is the term number and it must be an integer too. So n is a member of positive integers. All right. And what about this last one here? We're multiplying by, that's the first time we've seen a fraction. That's multiplying by neg-1/2, isn't it? Neg-1/2 every time. So here we are, here is our ratio of neg-1/2. So any term is the term before times by neg-1/2. All right. So where you have that multiply, we call it actually R for a ratio because we say that the ratio of any term to the term before is constant, so we're looking for that ratio. And then we could write it as any term is the term before times R. So that's a way in which we would do it. So in the IB notation, using mu, it would be like that. Okay, so that's Pearson's introduction there. So let's move down and have a look at the definition of the nth term of a geometric sequence. Now we've done it with recursion method here, but here is the actual explicit form here that. And this is from the IB information booklet, so let's use that one. Any term is the first term and multiplied by the ratio 1 less time than the number of the terms. Let's see if we can look at a bit of an informal proof for that. Here's our sequence, mu1, multiply it by r because it's geometric, multiply it by r again, multiply it by r. We can generate many terms here, and what would be the nth term when we get up here? It would be mu1 r to what power? Well, let's look at it. N equals 2, that's the second term. First term doesn't have any r's. The second term has 1 r. The third term there's been 2 multiplyings. The fourth term there's 3 multiplyings, so this is the nth term. That should be 1 behind it, so it should be n take 1. So if it's the nth term, seeing the first term didn't have an r in it, you're playing catch up. The r is 1 behind the number of the terms. Do you get it? Okay, so here it is. This is the line we want to use from the IBD booklet there, the information booklet using mu notation. So are you set to work with some geometric sequences? There's only the 2 formal types of sequences in this course that we study in detail. So let's come down and let's have a look at an example now. Find the geometric sequence with A1 equals 2 and R is 3. So what would it be? You could put some terms down. 2 multiplied by 3 you get 6, multiplied by 3 you get 18, multiplied by 3 you get 54. So in mu notation we'd say the nth term, first term, by r to the n take 1. So therefore mu n is, what's the first term? 2 times, what's the ratio? 3 to the n take 1. So we could get an explicit formula. An explicit formula, remember, says if you put in an n value, you'll go directly to that term. You can go to the 50th. In this case, what would mu 50 be? Here to be 2 by 3 to the 49. That idea. Go straight to the term and away you go. All right, so let's go to part 2. Describe the sequence like this. Well, it looks like it's being multiplied by -4 each time. So we say it's mu1 is 3 and the ratio is -4. It appears to be geometric from those first terms. So the nth term is, here it is here, should be mu(n) equals 3 by -4. Then take 1. You must put a bracket around the -4 because you've got to raise the whole of -4 to that power. Okay, describe the sequence here. 1 to a half, you're multiplying by a half, multiply by another half, you get a quarter. So it looks here as if it's mu(n) is the first term 1 by the ratio to the n take 1. Okay, so the terms are going to decrease, so they're going to get smaller and smaller. Okay, and the final one is to draw a graph of a quarter times 3 to the n take 1. So the first term is when n equals 1. So let's just work out some numbers here. mu1 is a quarter times 3 to the 1 take 1, which is 0, so this comes to a quarter. Okay, mu2 is a quarter by 3 to the 1, which is 3/4, etc. And so plotting it out, you could actually have used the TI here in graph mode, putting in this formula. And so you can see it's what we have already done if you watch the presentations in the order, and that is we did exponential logarithmic graphs. That's chapter 4 from Pearson's first of all. And we see this is an exponential function, isn't it, of the form y equals ab to some power x. So we expect it to look like this graph here. And indeed, I wonder if you'd like to think about the formulas we had for the geometric arithmetic, is mu1 plus n minus 1 times d. What did we get there? Well, we could have said y is some initial number, let's say a, plus d lots of n take 1. And because you've got a constant difference there, this is very much like y equals mx plus c, isn't it? Where there's a constant adder, the m, in front of the variable, and then a constant down the end. We expanded some of these and got a form more like this. So this is going to plot as a straight line because there's a constant difference between terms. Okay, so you will go up with a constant gradient, constant adder there. All right, so that's just some interesting linkages or threads with other areas of functions and graphs. So that's worth thinking about. Let's move down to another example and have a look. Example 8 here. Now we're starting to get into a practical situation, and sequences can help us with that. So at 8 a.m, 1,000 milligrams of medicine is administered to a patient. At the end of each hour, the concentration of medicine is 60% of the amount present at the beginning of the hour. So what proportion is left at noon from 8 a.m? Okay, so they haven't actually unpack this as much as I'd like to, because what we would have is 1,000 and then multiplying that by 0.6, isn't it? Only 60% remains. So this by 0.6, get the next one, and multiply by 0.6. Better put the multiplication in. So we're going down in quantity because the only got 60% remaining, so it's multiplying by 0.6. So this is geometric. The first term is 1,000 and the ratio is 0.6. So the end of end periods there, it'll be 1,000 by 0.6 to the end take 1. And here, what is n? N is going to be the number of hours here. So between 8 and 12, we will have 5. If we go from 8 a.m. till noon, that's going to be 4 hours worth of this. So that means n will be 5 terms. Okay, 5 terms. So this, strictly speaking, is wrong, where n is the number of hours. N take 1 is the number of hours. So really what they're trying to say is if 8 a.m. is n equals 1, then 9 a.m. n equals 2, and by the time we get up to 12, we're at n equals 5. Because remembering that we're starting with the first term being at 8 a.m. So 9, 10, 11 and 12 comes up to the 5th term, but only 4 hours have gone by. So this is actually wrong here. N is not the number of hours, because the number of hours is 4 hours have passed, but the number of terms it should be. So actually noon is the 5th term. 4 hours later, but in the first hour is term 1, and the 4 hours later is term 5. Okay, inclusive there. Okay, so the final answer is 1,000 times 0.6, don't forget the bracket, to the 4th. And then we can get that, and we should be quoting milligrams per, perhaps, but we can't do that, milligrams per volume or something. We can't really put the units in. Okay, so that'll be the number of milligrams, really. We should just have milligrams. It's the number of milligrams present in the bloodstream. We should have the units there. And usually we take that, and there's a funny answer here, we usually take that to 3 significant figures. In the IB, they usually print that on the front of exam papers, give answers in exact form or to 3 significant figures, or as required by the question. So we could leave it at that. We'll go, we'll go to 3 significant figures. If the second dosage is administered at 10 a.m, what is the total concentration? So the idea here, the second dosage there is going to be another 1,000, excuse me, and noon here then for the second dosage, at 10 a.m, so that is our n equals 1 then. Noon is actually n equals 3, and there's going to have 2 hours worth of decline, if you like. So to get to the 3rd term, there will be 2 lots of multiplications by 0.6. And linking back to the exponential work of chapter 4, of course we often think of this power as how many times the multiplier has been used. Number of times the 0.6 is applied, if you like. And so that gives you an idea of why it's 4 there, not 5, and over here, why it's going to come to 2, not 3. All right. So what's the concentration? Well, we had 129.6 from the original dose would have been in there. If we do it again, there'll be a total of 489.6 milligrams. All right, very good. Let's go on and look at some other things we can do with these. Oh, compound interest again. We have to put here, refer to chapter 4 because we've done it there. Refer to chapter 4. We did chapter 4 before coming back to doing sequences and series. Even though the topic order does have algebra, sequences and series there as topic 1. Okay, so we're putting money into an account, €1,000, and it's growing at 6%. So initially we've got 1,000. After 12 months, if it's an annual interest rate, we've got 1,000 plus 6% of 1,000, and we can factorise it. Then we're going to go on even further then. So we've got our amount after 1 year, and then that amount is multiplied by 0.06 again. And so the amount we've got, if you factorise this, is 1,000 outside of 1.06 squared. And then that amount, 1,000 by that, has got, we've got those two amounts, and then times him by 0.06. So you've got what you started with, and then that amount, you've got 6% of it. So you see what's happening. It's a factorisation problem. It's getting bigger and bigger. Then you start with that, and then you add 0.06 of it. You take out the common factor, and you've got 1.06 again. So you can see what's happening. It is going to be a geometric sequence because we are actually adding on 6% of what we had before each time, and that's going to produce that power. So you can see that this is what? Mu n equals mu by an r, which is 1.06 to the n take 1. It is going to be that type of thing. Now just watch the n take 1 in compound interest, because the first term is usually called 0. Come over here. 0 years, that's the first term. So the third term is 2 years worth, if you like. So the third term, the third term is 2 years, or 2 multiplyings by this. So just watch what you call the first term and so on in this sort of work. So here we have it in a formal statement. We start off with an amount which we call the principal, and then we're adding some interest, so it's 1 plus r as we saw before, and then squared, etc., and then to the t for the number of years. So the general form is generally this: the amount after a certain time is the initial amount, and then this is the decimal rate of growth, like 1.06 it was before. You've got all you had before plus 6%, and this is the number of times you do it. And now, of course, if you are doing it more than once a year, you need to adjust the interest rate. So the interest rate would be, let's say you're doing it quarterly, that's 0.066% per annum divided by 4 would have to go in there. And up here, the total number of times you would be applying it, you'd be doing it 4 times a year times the number of years. So we've seen this in chapter 4 with the exponential function, and the same thing is applying here. So we have an overlap between those two sections, an important overlap. The exponential function always, of course, can be considered to represent a geometric sequence. Remember why now, because a geometric sequence looks like this. And so you have a number out the front here, like of the form of a exponential function. You've got number out the front, some value here, some constant raised to a power. So very, very similar behaviours there. And if you plotted the terms in a sequence, you would obtain, as we saw before, you're going to find they're going to go up like that. Or, of course, so this is mu n and n here, but of course they could come down as well if it was a fraction for our ratio. So start to put those things together. They're interesting themes or threads running through the course. All right, let's come down now. Have a look at another example. Another one, compound interest, 6%, and compounded annually, quarterly and monthly. So let's just adjust this ratio between terms now. Thinking about it as a sequence, and of course you'll do it once a year and it will be 6%. If you do it quarterly, adjust the ratio of growth, and how many quarters in 10 years? 4. And then monthly, you've got to change the ratio there and the number of months. All right, so very common with the sequences, with the exponential function work. Okay, come down now and let's look at population growth. Of course, this is starting to overlap significantly with exponential functions because they are the same sort of thing, of course. So here we are. City of Baden in Lower Austria grows at an annual rate of 35%. If the population of Baden was 23,140 in 1981, what would it be for 2011? Okay, so doing it from a sequence point of view, you would say, well, right, here we are, mu1 is 23140. The ratio of growth growing by 0.35%, so that's got all the people we had before and 0.35%. So that's our ratio. Now we want to go from, let's do this, 1981 to 2011. Now 2011 take 81 is 30 years. 30 years. But therefore, counting this as mu1, this will be mu31, counting the ends inclusively. So doing it from a geometric sequence point of view, remember mu n, we want to be mu31 equals mu1 times this ratio to the n take 1, 31. Remember, there's a 31st term. Here, take 1 is 30. So you've got to watch the term numbers here. Okay, so using the formula, remember, mu n is mu1 plus, times mu1 times r to the n take 1. So that's why this power will be 30, not 31, because our term in that final year of 2011 is equivalent to mu 31. That's the problem. That's the problem there. So what's that? Now, if you want to do it from an exponential function point of view, it may actually be easier because the function is the population at time t is the population at time naught multiplied by, now how many times do you apply this growth factor? You could put t there for the number of years. Now, doing it that way, we don't have this confusion with the 30th or the 31st term, because it would be 23140 times 1.0035. How many years of growth have been applied? Only 30. Okay, so you get the same power. But in the exponential function approach, you're thinking about how many times do you apply this ratio. So up here you're thinking about the number of multiplications by 1.0035. So interesting, different ways of looking at the same actual mathematics. Okay, so they mention that here in chapter 4. about the overlap and talking about exponential functions. Just notice there, you'd put that on the calculator, and there we would have the projected growth there in 2011. All right, let's continue on. And here's some for you. I think there are 18 problems. Yep. So let's go up here. Now just watch this note. As with the arithmetic means idea, if they say put in geometric means between two, then we're talking about a geometric sequence. The same idea working with a geometric mean. The other way of simply saying it in this first question, insert 4 terms in the geometric sequence between 3 and 96. So they could just say that more easily, and that's what they usually do in the standard level course. Say, create a geometric sequence, put in 4 terms between these two, or something like that, or call 3 the first term, and then 96 would be the 6th term if they want 4 terms in between. So you're going to do that in a very, very similar way to what we did the arithmetic ones. So let's just have a look. There's the first 15 questions. So freeze that and have a go. And the answers that will be down underneath these questions as before. And then we'll put up the rest of them there. You can freeze that and work through. So I'll go down and show you the answers now. So here's question 1, most of the parts, 3, 4 and 5. I'll freeze that bit. Then the rest of question 1 down to the end of H there, and that goes through to the end of question 8. So freeze it at various stages there. And then we go to 9, 10, 11, almost all of 12. And coming down to 12, 13, 14, let's finish that off. We're nearly getting there. 13, 14, just finishing off. 15, 16, 17, 18, I think we can get on there. Okay, so they are all the answers. I'll go back up and take it back up to the problems now, and just leave that at the beginning of those problems. So enjoy yourself. It's getting interesting, isn't it? We're looking at analysing some particular examples of sequences, namely the arithmetic and geometric. But just keep in mind, in any exam, they could give you a recursion formula of any particular type. These are the only 2 sequence types that we work with, an explicit formula and a recursion formula. So have fun building up your skills, but for now, it's cheers from me. Catch you in the next presentation. It's part 4. Do you know what it's about? You'll have to wait and see. Cheers for now.